Okay, so the next segment is going to be about lexicalized parsing. So lexicalized parsing is one step up from context-free parsing because it allows us to capture some regularities that are involved with specific words and specific heads of phrases. So why are we even considering it? Well, the reason is that PCFGs and CFGs in general have some limitations. For example, the probabilities don't depend on the specific words. If we have a verb like give and a verb like see, we know that they have different structures. So give takes two arguments in the form give someone something versus the verb see, which only takes one argument, as in see something. In context-free grammars, it's not possible to take into account this kind of argument structure easily. It's also not possible to disambiguate sentences based on semantic information. So for example, the fact that eating pizza with pepperoni is very different from eating pizza with a fork, because pepperoni is a food item, whereas fork is a tool. So we cannot, in a context-free grammar, figure out that pepperoni is more likely to be associated with low attachment versus a fork, which is high attachment. So the basic idea of a lexicalized grammar is to use the head of a phrase as an additional source of information. For example, instead of having a rule that just says that the verb phrase gets transformed into a verb, we're going to have a rule that says a verb phrase whose head is 8 is going to be transformed into a verb whose head is 8. So here's an example. We have the parse tree from the previous segment for the sentence, the child ate the cake with a fork. We want to convert this into a lexicalized form, and this is done by starting from the lowest level of the parse tree, the terminal symbols in the words, and by extracting the heads of every constituent in a recursive way until we reach the top of the sentence. So we're going to start with the individual words. So the phrase the cake is a noun phrase, and the rule for a noun phrase says that the head of the noun phrase is equal to the head of the noun. So since the head of the noun N2 is cake, the head of the entire noun phrase 2 is also cake. Same thing happens with the fork. The head of the noun phrase labeled noun phrase 3 is going to be fork because its main noun is fork. Similarly, the head of the noun phrase 1 is going to be child because the head noun is child. So at this point, we still have to expand several more heads. So the head of the prepositional phrase with the fork is, by definition, the preposition itself. So we're forgetting about fork at this point, and instead we are replacing it as the head of the prepositional phrase with the word with. The head of a verb phrase is the verb. So the verb phrase ate the cake is going to have 8 as its head. And this 8 is going to be propagated one more level up to the next VP up, which is also going to have 8 as its head. And now we have two choices for head for the entire sentence. Child, which is the head of the noun phrase, and 8, which is the head of the verb phrase. And in this case, which one do you think wins? Well, the rule is that the head of the sentence is the head of its main verb phrase. So we're going to propagate 8 as the head of the entire sentence. So every production in the grammar can now be rewritten as in lexicalized form. For example, the rule on the top is going to be S headed by 8, gives us NP headed by child, followed by VP headed by 8. Okay, so one of the most popular parsers that involve lexicalization is the Collins parser. The version from 1999 is the one that I'm going to use as an example. So this model is generative, and it has the following types of rules. Every left-hand side is turned into a sequence of L's, an H, and a set of R's. L's are the things that appear before the head. R's are the things that appear after the head. So the generative model goes as follows. H gets generated first. Then all the L's get generated right to left from 1 to N. And then finally all the R's going left to right from 1 to M. So the probabilities are estimated using maximum likelihood estimation from the Penn tree bank. So here's an example. We want to find the conditional probability of the preposition of given the verb think. Of is labeled as in, as the preposition in. And think is labeled as a verb, and we're just going to compute this probability by dividing the actual occurrences of the word of to the right of the head think divided by the total number of symbols that appear right of the head think. And we can also do some sort of smoothing if the data is sparse. So the smoothed probability that involves the lexicalized version of given the lexicalized version of think is going to be a linear combination of three things. One, the actual counts for of and think lexicalized. But if those are not available, we can also look at the case where of is lexicalized, but the verb is not. And finally, the case where none of them are lexicalized. So this helps us address some of the issues with lexicalized grammar, specifically that the training data is much more sparse when you train a lexicalized grammar because of the so many different combinations that you have to take into account. And that leads to a combinatorial explosion, and you need to parameterize the grammar. So one technique that I want to bring up here is called discriminative re-ranking. It's a technique that is used because very often in a probabilistic context-free grammar, you can have many parsers associated with the input sentence, and their probabilities may be very similar to each other. So it's not clear if you wanted to pick just one of them, whether the one with the highest probability is the best one. Instead, what you do is you produce an n-best list, and you use some additional information to pick the parsers that are most likely to be the best ones. So some of the considerations that you take into account on this n-best list is things like the parse tree depth. So you want to make sure that you don't get sentences that have trees that are too deep or too shallow. You also take into account whether you have more instances of left attachment or right attachment. So for example, in English, it's more likely to have right attachments than left attachments. So you would rule out a parse tree that has too many left attachments. You can also look at the discourse structure. So for example, if a certain sentence is the second one in a paragraph, you may want to treat it differently because it's more likely to include anaphoric expressions that refer back to the previous sentence. So can you think of some other features that can be used in the re-ranking? Well, let's see. So the question was, what other considerations can you have for re-ranking in addition to parse tree depth, attachment, direction, and discourse structure? Well, some of them are consistency across sentences. So for example, you may have a word that was interpreted in one way in one sentence. You want to ensure that it's interpreted exactly the same way in the next sentence. You can also take into account some information that comes from some of the other stages of the natural language pipeline, for example, the part of speech sequence or some constraints from speech recognition. One thing that you may be wondering is how well do parsers work? Well, here's some examples. The F1 measure computed on sentences that are 40 words or less. This is a standard evaluation metric for statistical parsers. Here's some statistics. The ballpark is in the low 90s. So the earliest parser that I'm going to show here is the Charniak parser from 2000. This one achieves 90.1% F1. And there are some modified versions. For example, a better version of the Charniak parser is by Charniak and Johnson from 2005. It achieves some of the highest possible performance on F1, namely 92%. So this concludes the section on statistical parsing. In the next segment, we're going to look at a very different type of parsing called dependency parsing.